Okay, here we're going to talk about how we actually determine the deflection curve of a beam, and we do this using integration. And the way we're going to start is by relating the curvature of the beam, the radius of curvature of the beam, to the bending moment. Okay, so we take out a small dx here, we apply a bending moment to it, or we know the bending moment at that point. Okay, so before deformation, dx and ds are the same. Okay. After which, if I look over here, right, along the neutral axis again, there's no normal strain, okay? So that ds equals dx equals the radius of curvature times d theta, that arc length down here. Now ds prime, some point, a distance y above, is just going to be rho minus y times d theta to get that relationship. So then I can find the strain, okay, at that point, okay, the ds prime minus ds over ds, okay. That strain is going to be plugging all those in. I get a rho d theta that cancels, manipulating things a little bit, okay. Actually, all my d thetas cancel, the rhos. Anyway, rearranging things, I get 1 over rho equals the strain over y, and that's times a negative. Okay. Now, using Hooke's law, which again, the strain is equal to the stress over the Young's modulus. Stress due to a moment we know to be negative my over I. Okay, and I can relate the radius of curvature to the moment given by that equation. 1 over the radius of curvature equals m over the modulus times the moment of inertia. Okay. Now, to find the elastic curve, we use this equation, which apparently is given in many textbooks, calculus textbooks, that relates rho to the elastic curve. The elastic curve being what we're calling v, and that's a function of x as I move along the x-axis. Okay. Simplifying this down and getting rid of this higher order term, which is the derivative squared, so getting rid of that higher order term and just sticking with the numerator here, I get the second derivative of the elastic curve equals 1 over rho. Okay, so from that I can set my moment equal to EI times the second derivative of the elastic curve, which means if I can find my moment, I can integrate it twice to find the elastic curve. And then using our relationships we had before when we talked about shear and moment diagrams, the shear is the third derivative of the elastic curve, and then an applied load would be the fourth derivative. The way we'll typically do it is find the moment and then take integrate it twice to calculate it out. Now when I integrate, I get constants of integration. So I use both boundary conditions, which would basically be a value of something at a particular point. And I have some examples here where the deflection on a roller is 0. I know the moment here would be 0. Okay. Again, at a roller, the deflection is 0. Something like a fixed end, the deflection is clearly 0. But also the slope is 0. That would be the first derivative would be 0. Okay. At a free end, both the moment and the shear force are 0. So I have these different things based on how things are set up at a specific point. We call that a boundary condition. The other thing I have is a continuity condition. And this is because, remember, when we find our moments, we have to cut in a few places. Okay. Well, at the intersection, at that discontinuity, where I switch from one variable to the next variable, or one coordinate to the next coordinate, okay, the displacement and the slope have to be equal to one another. Otherwise, you're going to have a bend, a sharp bend in the beam, or the beam can't be in two places at any point. So we use these boundary and continuity conditions to find those integration constants that come from taking a couple of integrals of my moment function. So if you go to the example problem on beam deflection, this should clear up any questions that you might have, and you can see the process on exactly how we do this.